Here is the question that I asked at the end of the previous part of this video lecture, and the options I've given you, except for the correct one, all contain errors that I frequently see students make when they're drawing field lines. So let's go through them. First of all, D. D cannot be right because that field line actually isn't complete. There's no arrowhead on it, and so we don't know whether it's representing, say, at this point, that the field points this way, or the other way along the line. Without the arrowhead, we can't tell, and so this is ambiguous and can't possibly be correct. But there's another reason it can't possibly be correct. At that point, the fields due to the individual charges would look like this, and the total would be their vector sum, which would look something like this. And that isn't tangent to the line, so again, it can't be right. B has sort of a similar problem. It's got two arrowheads on it, but they point different ways along the line. And so again, if you think of this point, it's unclear whether the field there points this way or this way, and so it's ambiguous and it can't be right. There's also another thing wrong with it, and it's similar to what's wrong with A, or one of the things wrong with A. So let's look at that same point, but with A. Again, the fields due to the individual charges would look like this, and so their vector sum would point straight to the right, and that isn't tangent to the line, and so it can't be correct. But we didn't even need to do that to see that A can't be right. Field lines have to start on positive charges and end on negative charges, but this diagram is showing a field line that starts on a positive charge and also ends on a positive charge. That can't be right. And so we're left with C, and I'll leave it up to you to just check a few points along it and the direction that the field ought to point at those points, and verify that it's consistent with the way this line is drawn. So I'll draw a more complete field line diagram for this pair of charges. And one thing about field line diagrams is that it's much easier to quickly draw a nice complete representation of a field using them than it is with a vector field diagram. So first, I need to decide how many lines are attached to each charge. And this is an arbitrary choice. I'm going to choose 8. So I'm going to put the stubs of 8 lines on each charge, because these charges have equal magnitude, and so the same number of lines will be going into or out of each of them. And now I'm going to fill in the line that I already drew, like so. And now I'm going to follow the same sorts of rules. This line is easy. Everywhere on the line connecting these two charges, the field must point directly to the right, and so there must be a field line that passes through here. And by symmetry, I can see that there must be another one that comes this way. Similarly, as I come out here, at every point, there is the field points out away from the positive charge, but in away to the negative charge, and so the total force will always be a little bit in towards the negative charge, and this line must curve. Eventually, by the time I get here, the total field must point directly to the right, and it must come over, and these lines must connect up. And now this line would come out and again curve slightly towards the negative charge. It will wander off the page. It would continue way out and come back in somewhere over here. And this line would go straight out, because everywhere on here there is a field pointing out due to the positive charge and a much weaker field pointing the other way due to the negative charge, and so the total electric field is to the left everywhere here, and so we just get a straight line, and there would be a straight line coming in here. So notice these lines leave the diagram. However, the total number of lines leaving the diagram is 0. See? 3 leave, but 3 come in, and so the total leaving the diagram is 0. Note that the total charge here is 0, and that's always going to be true. The number of lines leaving the diagram will always be proportional to the total charge. Now I'll draw one for an unequal pair of charges. So this charge has twice the magnitude of charge of this one. And so notice I have drawn 8 little stubs of lines on it, but only 4 on the other, because the number of lines coming into or out of a charge has to be proportional to the number, the amount of charge on it. And so again, there's going to be a line that goes straight here, because the field must be tangent to the line at every point, and the field is certainly straight to the right everywhere in between these two charges. And then similarly, this line is going to come out and connect over here. And there's going to be a line that goes straight off to the left out of the positive charge, and a line that comes straight in from the right to the negative charge. But notice that there are no stubs left to connect on the negative charge. And so these other lines will simply head off to infinity. However, they are curving because of the influence of the negative charge, right? At this point, the field would not point straight away from the positive charge. There would be another piece of field pointing in towards the negative charge. So note that now we have 5 lines out and 1 in, so a net of 4 lines out. And that is not a surprise because the total charge here is positive, and so we must have overall a net number of lines that leave the diagram. I just want to finish off by contrasting field line diagrams with field vector diagrams. One big difference is that in field vector diagrams, since you're drawing a vector at each point where you're choosing to draw one, you can see the strength of the field at each point by looking at the lengths of those vectors. How do you see the strength of the field in a field line diagram? Well, note, we know that the field must be getting weaker as we move farther away from these charges. And one thing to notice is that farther away from the charges, there's a lot of empty space on the diagram. Where the field must be very strong is in between these two charges, where there's a field roughly pointing to the right due to the positive charge, and also to the right due to the negative charge, and so the fields are tending to reinforce each other. And notice that the field lines are very close together in here. And so this is how you see strength of field in a field line diagram. It is proportional to the density of the lines in the region.